This lecture will focus on simple harmonic motion and springs. In nature, one finds that there are some motions that are repetitive. For example, a mass on a spring can be set into motion by simply pulling down on it and releasing. The mass will bob up and down between two maximum displacements in a repetitive motion. We describe this motion as oscillatory motion or periodic motion. Any oscillator undergoing periodic motion can be described by certain mathematical properties. The time for one complete oscillation is called its period, t, and is measured in seconds. The number of oscillations it makes every second is its frequency, f, and is measured in seconds to the -1 or hertz. A spring makes 10 oscillations in 30 seconds. Its frequency, f, would be 10 oscillations divided by 30 seconds, or 0.33 hertz, and its period, t, is the inverse of the frequency, 30 seconds divided by 10 oscillations, which is 3 seconds. So far, we have considered constant or uniform force. Now consider the force needed to stretch a spring. The more you stretch it, the harder it is to stretch. This is because the force required to stretch depends on the amount of stretch you have given the spring. The force changes with stretch. It is not constant. Also note that the force is directly related to the stretch. If you put twice the mass on the spring, it will have twice as much stretch. Hooke's law for springs states that the force increases with the amount the spring is stretched. Robert Hooke was noted for his study of elasticity in springs. He determined that the force needed to stretch a spring was equal to the stretch x times the stiffness or spring constant k of the spring. The spring constant is measured in newtons per meter. If the force needed to stretch a spring is kx, then the restoring force, or the force that the spring pulls back with, is F equals negative kx. In this image, a mass on a spring is oscillating back and forth. It moves from a maximum displacement of A through the equilibrium point at O and to the other maximum displacement at negative A, and then repeats its motion. If there is no friction, then the mass would continue this motion forever and ever and ever. It is called a simple harmonic oscillator. What would a graph of position or displacement versus time look like for a simple harmonic oscillator? It would look like a cosine graph, because at t equals 0, it would start at its highest point. If we call the period of the motion t, this is the time to complete one full cycle, we can write the position as a function of time. X equals the amplitude times cosine of 2 pi over t times the time. A mass is placed on a spring and it's set into oscillation. The position is given by x equals 4 centimeters cosine of 6.28 t. What is its amplitude? It is simple. The coefficient of the cosine function is the amplitude, 4 centimeters. What is its period? We can use the term inside the parentheses to find the period. 6.28 equals 2 pi over t. T equals 2 pi over 6.28, which is equal to 1 second. An object in simple harmonic motion has the same motion as one component of an object in uniform circular motion. You can see that the peg moves back and forth through maximum displacements and equilibrium points, just like the spring does in this example. In circular motion, we learned that the angular frequency of object, which is measured in radians per second, angular frequency, omega, or W, equals 2 pi divided by the period. Since the position function is a cosine wave, and we usually take cosine of radians instead of degrees, the position formula uses angular frequency instead. Position equals A times cosine of an angle. In this case, for a simple harmonic oscillator, position equals A times cosine of omega t. Angular frequency is related to frequency as well. Omega equals 2 pi f, or omega equals 2 pi over period. A mass is placed on a spring is set into oscillation. Its position is given by x equals 4 centimeters cosine of 6.28 t. What is its amplitude? This is read easily from the function 4 centimeters. What is its angular frequency? The angular frequency is also read easily from its function, 6.28 radians per second. What is its frequency? We will use the formula for omega to find f. Omega equals 2 pi f, so f equals omega over 2 pi, or 1 hertz. What is its period? Its period is the inverse of f, which is also 1 second. Now let's consider what the velocity function would look like for a simple harmonic oscillator. First of all, the oscillator would have the most velocity when it moves through equilibrium. It would have zero velocity at the endpoints. So if you take the slope of the position graph, you will see that the velocity graph looks like a negative sine graph. The oscillator experiences the most acceleration at the endpoints when it changes direction. If you take the slope of the velocity graph, you will find that the acceleration graph looks like a negative cosine graph. The velocity function is v equals a times omega, negative a times omega sine of omega t. The acceleration function is a equals negative a omega squared times cosine of omega t. Both of these are found by taking the components of circular motion quantities. Notice that the velocity amplitude will fluctuate between plus or minus negative a omega. This indicates that the maximum velocity for any simple harmonic oscillator is always a times omega. The acceleration amplitude fluctuates between positive and negative a omega squared. This indicates that the maximum acceleration is a omega squared. A mass is placed on a spring and is set into oscillation. Its position is given by x equals 4 centimeters cosine of 6.28 times t. What is its velocity function? Plugging into the formula for velocity, we'll get velocity equals negative 4 centimeters times 6.38 radians per second times the cosine of 6.28 t, which gives us negative 25.1 centimeters per second times the cosine of 6.28 t. What is its maximum velocity? It's just 25.1 centimeters per second. What is the acceleration of the function? Using the acceleration formula, we get acceleration equals negative 4 times 6.28 radians per centimeter squared times sine of 6.28 t. That gives us an acceleration function of negative 158 centimeters per second squared times the sine of 6.28 t. What is the maximum acceleration? The maximum acceleration is simply 158 centimeters per second squared. Since the force on a mass of a spring is proportional to its displacement, and also to acceleration, it turns out that there's a relationship between omega, the spring constant, and m. Omega squared is equal to k over m. A mass is placed on a spring and is set into oscillation. Its position is given by x equals 4 centimeters cosine of 6.28 t. If the mass on the spring is 200 grams, what is the spring constant? Using our formula for omega squared, we will solve for k. Omega squared equals k over m. So K equals omega squared times m. 6.28 radians per second squared times 0.200 kilograms, making sure that mass is in kilograms, gives us a K of 7.9 newtons per meter. The total mechanical energy is also conserved in a simple harmonic oscillator. That means that at any point of the oscillator's motion, the sum of its kinetic energy and potential energy is always the same because there is no friction in the system. So the total energy is constant. As the kinetic energy increases, the potential energy decreases, and vice versa. The oscillator will have the most Ke when it has its maximum velocity at the equilibrium point and its most Pe at the endpoints when it stops. This diagram shows how the energy transforms from potential to kinetic and back while the total energy always stays the same.